Hello everyone, welcome back to the channel. So today we are going to talk about one of the most important concept in deep learning, that is backpropagation. Now I'll tell you this in a very simple way. Okay, so think of it like you are playing cricket and you throw a ball, but you miss the target completely. Now what you do? You'll don't throw again randomly, right? You'll think first, what was my waist and how was my shoulder angle and everything, where were my fingers, and then you will throw it back and then see that what went wrong. This is exactly how back propagation works. When the network make wrong prediction, back propagation goes backward through the network and say, okay, which weight were responsible for this mistake. They calculate this, take the exact weight and see the contribution to the error. Now here is one thing that you need to remember that is super important. Backpropagation does not update the weight itself. It calculates the gradient, means it figures out the direction and the amount of changes need. The actual updating that is being done by the optimizer, like the gradient descent or the Adam. Okay, moving forward towards the next step, we can see that how it actually works. So they are divided into two phases. Phase 1, the forward pass, and the phase 2, the backward pass. So in the phase 1, data enters the network from left side, the input layer. It travels through each layer one by one. At each layer there happen two things. First we calculate something called as Z, that is basically the weight sum of the input plus a bias. So Z equal to W times A plus B. Then we pass Z through an activation function like ReLU or Sigmoid, and we get a at the output layer. And the most important part is that we save these values. We catch we put them in a memory because we are going to need them later in the backward propagation. At the end of this, the network gives us a prediction. Let us call as y hat. Then we compare the actual answer y, and then we calculate the loss, basically what went wrong here. In the phase 2 of the backward pass, this is where the magic happens. We start from the output layer and move backward right to left. At the output layer we calculate the error signal called the delta. This tells us that how much the output layer contribute to the mistake. Then at each layer going backward, we'll do two things. First, we calculate the gradient for the weight and bias of the layers. The formula is W equals to delta times A transpose of the previous layer, simply the output product. Second, we pass the error back to the previous layer. The formula is delta of the previous layer equal to W transpose times current delta, multiplying element wise by the derivatives of the activation function, and then keep doing this layer by layer all the way back to the beginning. The whole maths about the chain rule from the calculus. Basically you have a chain of functions. The total derivative is just the product of all the individual derivative. Okay, let's say we have a neuron. Input x is 2, weight w is 0.5, b is the bias, and the true answer y is 1. So the forward bias z equals to 0.5 times 2 plus 0.1 equals to 1.1. Now we applied the sigmoid. We get y hat equals to roughly 0.75. So the loss equals to half of 0.75 minus 1 square root, that is squared, that is 0.031. In the backward pass, gradient of the loss with respect to y hat equals to 0.75 minus 1, that is equals to minus 0.25. So the sigmoid derivative will be 0.75 times 0.25, that means 0.1875. Now the gradient with respect to w equals to minus 0.25 times 0.18275 times 2 equals to minus 0.09375. So weights are updated with a learning rate of 0.1, and w becomes 0.5 minus 0.1 times, so it will be 0.5094. Okay, see, the weight increases slightly because the prediction was too low, but we push it up, then the gradient descent will work perfectly. Now we have section 3 that contain vanishing gradient or the optimization and some of the key takeaway. So now the problems are, problem 1 is the vanishing gradient. Remember that every single delta travels backward in very deep network. It passes through many and many layers. At each layer it gets multiplied by the derivative of the activation function. Now if we use sigmoid function, then the derivative is almost 0.25. so at every layer the gradient gets multiplied by something less than 1. So 10 to 15 layers after, the gradient becomes so tiny, almost zero, and the early layers learns absolutely nothing. So this is the vanishing gradient problem, which we have already discussed about. Second is the exploding gradient. So the opposite problem, if weights are very large, the gradient grow exponentially as it travels back. Loss become NaN. Training catches completely wrong data and it crash down. So the fix is the gradient clipping. You just have to cap the gradient at the maximum value. If the gradient norm goes above a threshold, then your scale is down. Simple as that. Okay, we have seen about optimizers also. Plane gradient descent is one of the, but it is very slow. SGD with momentum adds a velocity term. It build up the speed in the right direction. We have RMS propagation also. RMS prop adapt the learning rate based on the recent gradient. And the Adam, which is one of the most popular one. It combines both momentum and the RMS prop. It updates the learning rate for each parameter individually. Okay, so now the default representation is that for Adam with learning rate 0.001, this works very best for almost everything. Okay, now we have some of the key takeaway that the backpropagation compute gradient by applying the chain rule backward through the network. It has two phases: forward pass to compute and catch value, and backward pass to propagate gradient. Second, we have the vanishing gradient. It uses ReLU and residue connection. Then we have the exploding gradient, which use gradient clipping, which we have just discussed. Backprop only compute the gradients, and the optimizer does the actual weight update. In practice, PyTorch and TensorFlow can handle them automatically also. So this is how we have covered the complete backpropagation basics. We'll be doing the coding part soon also. Thank you.